One quick note for everyone on this webinar, if you have a question throughout the session, please use the Q&A controls in Zoom control and ask your question. We will make some time towards the end to answer these questions live. And if we run out of time for whatever reason here, we'll make sure that we answer this offline. So with that, let's get started. So we have a very interesting session lined up for you. The focus of this session is first, we'll go over the scenarios where using a distributed SQL database like Aurora DSQL or YugabyteDB makes the most sense. And then we're going to do a deeper dive into both the architectures, both the databases, do a contrast and comparison of the feature set, and kind of outline for the viewers here, when is each database a good fit for what kind of use cases. Before we go any further, I just wanted to give a quick shout out to AWS. This is a competitive session, but AWS is a great cloud service infrastructure partner that we work with. And YugabyteDB is designed to work flawlessly on AWS infrastructure. Our fully managed offering is supported in more than 23 AWS regions worldwide. There is AWS Marketplace listing for YugabyteDB, and you can subscribe using this Marketplace listing, both using a monthly subscription, pay as you go, or you can go for an annual subscription. And YugabyteDB interoperates really well with all of these AWS services, which are powered by AWS. And then we do have the partner certifications for Graviton, Private Link, and so on to make sure you get the best experience on AWS. So with that, let's launch into the meat of this webinar. So first things first, if you are a database architect or a developer tasked with picking a new database, or maybe moving your existing database to a modern one, there are some common challenges that you'll run across, and we are just going to take an overview of what those challenges might be. So the first challenge is the developer experience, right? Do I need to learn a new SQL language? Do I need to learn a new API? Will the database work with the existing tools and ecosystem frameworks that I use? Another one is, where can I deploy it? Are there any restrictions in terms of where it can be deployed, whether it's cloud or a deployment model? Can I do it on containers, Kubernetes, VMs, and so on? Another consideration is scalability. Eventually the user base for any application is going to grow. So how do you scale your reads and writes seamlessly to handle the traffic? Does it require you to do any additional handling in the application, such as manual sharding, manual partitioning? And then as the data grows, as your customer base grows, how do you make sure that you maintain low latency? Cloud outages are inevitable, and this can happen in the form of hardware failures, or it could be natural disasters or catastrophic failures, which bring the entire data center or regions down. Though it might seem rare, they happen quite regularly if you look back at the history. So how do you deal with these outages when they happen and make sure that your application doesn't go down or remains available as per your requirements? Another one is, how do you make sure that, in case of a catastrophic failure, like the entire data center going out or a region going out, how do you ensure DR in those scenarios, right? And in some cases, this is not even optional. In some cases, regulations mandate this in certain geographies. And then the third one is, as your data grows, you might have a user base spread across the world. And how do you present a consistent view of your data to the users, regardless of wherever they are? And finally, how much complexity do you want to take on, and how much do you want to delegate to the database, right? So do you want to manage the complexity yourself in your own application or on your end by managing multiple databases? Or how do you decide to stay compliant with any data residency regulations that might be in effect based on where users reside? And then there's always a trade-off in database design. So sometimes, depending on the database that you are looking at, you might have to make some hard trade-offs between strong and eventual consistency. So all of these considerations go into picking a database, and we have distilled down some scenarios where picking a distributed SQL database like Aurora DSQL or YugabyteDB is a better choice than going with a more traditional database. So let's look at some of those scenarios. So if you're dealing with large data sets, or if you're dealing with dynamic workloads where vertical scaling is just not going to cut it, then distributed SQL database is usually a good answer. And this is because most distributed SQL databases have the ability to scale your data horizontally by doing automatic sharding, automatic replication, and it accounts for rapid growth and unpredictable spikes in an application. Another good reason to look at a distributed SQL database is if your users are geographically spread out, and if you need to provide them low latency access regardless of where they are on the globe, right? Because the last thing you want is provide a different user experience based on where the users are located. So to provide a consistent user experience, it's must that your database is capable to distribute the data and move the data closer to where the users are. And sometimes this also comes with the baggage of complying with the data residency laws, which might exist in those regions. Third one is resiliency. As we discussed on the previous slide, outages are going to happen. That's just the reality of life. So how does your database respond to those failures and outages when they happen? And distributed SQL databases typically avoid single points of failures in their design. So that makes them a great candidate for building a resilient solution. Another one is, before we go to the next slide, another one is how do you approach common maintenance operations like OS upgrades, database upgrades in your database solution. So picking the right solution, make sure you don't have any downtime during those operations. And finally, it's just reducing complexity, right? If you want to simplify your experience and focus more on your core application rather than the surrounding things like doing manual sharding or doing replication yourself, then that's a good reason to look at distributed SQL databases, because they can handle a lot of this work on the database layer, and then you don't have to worry about it in the application. It just simplifies your user experience. So with all of those reasons, now that we have laid out the foundation for when distributed SQL databases are a better candidate, let's take a look at some of the concrete examples. So I'm going to invite Anand to talk about our first distributed SQL database that we are going to cover today, which is Amazon Aurora DSQL and other offerings in the Aurora family. So take it away, Anand.
Thank you, Shreyas. It's great to be here. Good morning, good afternoon, everybody. To get started, I'll have a small disclaimer. All of the information that we're sharing today in today's session is from the publicly available sources. Okay, for those who are not familiar with the different Amazon Aurora offerings, here is the list. And features listed here in this table is not a comprehensive list of features supported by these services, but these features are very relevant to our talk today. Okay, let's start with Postgres compatibility. As you can see, RDS and Serverless V2 are most compatible with PG, as it literally runs PG instance within. But as we go through Aurora Limitless and DSQL, these services are designed for scale and distributed features. So that comes with some design choices and trade-offs that could reduce overall PG compatibility, at least as of now, but it could change in the future as they improvise on that. When we go to architecture, RDS is a serverless. RDS and serverless are single writers, while Limitless and DSQL addresses the limitation with multi-writer support. A thing to note is DSQL supports multi-writer across regions. And deployment time, RDS supports a provisioned dedicated instance, while serverless supports both provisioned as well as serverless, but we are talking about for this session, we're focusing on serverless. Aurora Limitless supports serverless, and DSQL also serverless mode. While serverless is great for scale up and scale down quickly, thing to note is that scale down to 0 could cause cold start latency issues. That is something to be aware of. Let's go to scaling. RDS allows manual vertical scaling, while serverless introduce auto horizontal scaling for reads, and Limitless improvises on that with horizontal scaling with read writes within a region. And DSQL supports horizontal scaling across regions for a read write both. When we go to replication time, RDS supports sync and async replications, while serverless Limitless supports async replication with up to 15 read replicas. DSQL supports synchronous replication between availability zones and regions. When we talk about zero downtime patching, RDS doesn't support zero downtime patching, ZDP, while serverless and limitless services claim they support ZDP, but supports with the best efforts. It means they do have caveats. It requires a downtime when OS and security patches time window. And we all know that it's very common maintenance activity in database. DSQL supports ZDP, zero downtime patching. Let's look at Amazon Aurora's architecture. It is a decoupled architecture with the flexibility to independently scale its components. This architecture limits a single writer node that handles all the writes for the database, offers multiple read-only nodes that receives data from writer through async replication. It offers distributed storage, which is essentially a collection of SSDs across AZs for availability and durability. And it supports scale independently compute R storage in this architecture. Let's look at some pros and cons of Serverless V2. It offers highest PG compatibility. As we discussed, it simply deploys and runs PG under the hood. User can scale read traffic by creating additional or more read replicas in this architecture. It has the resiliency for node and zonal failures within a region. This service is good for read-heavy applications. However, some limitations are, while read replicas are great for stale reads, but thing to note is that it's not great for consistent reads. If your application needs consistent reads, something that you should, be aware of with this service. Scaling rates is hard, due to its limitation in single writer architecture. And major DB version upgrades and other maintenance could cause downtime during those applications. So if your application, cannot tolerate downtime, Serverless V2 is not for your application. It doesn't support geo-partitioning, and it doesn't support strong consistency across regions. It can only support eventual consistency. And so where can we use, where can this service be used? It is suitable when some downtime is acceptable for your application, like non-critical workloads. For example, social media feeds or IoT sensor data. And it is suitable for, read-heavy workloads. For sure, it's a good fit if your application can handle just vertical scaling, right? And it also good fit for ephemeral workloads like test dev environments, something you can quickly spin up and shut down needs, right? In a nutshell, this service is a good for a simple, predictable, and read-heavy workloads. In this architecture, single writer becomes bottleneck soon for a serious workloads. Let's look at Amazon Aurora Limitless architecture now. This service addresses the scale problems that we talked about earlier through its auto scaling and sharding. At high level, this service architecture includes shards and routers. It offers managed sharding. It's basically simplified way of shard management. Two important components to note in this architecture: routers and shards. Routers essentially manages the metadata of shards, handles SQL connectivity, routes SQL queries to appropriate shards, and ensures consistency across the system, while shards stores the partition data. It also supports the DB shard group. It is essentially a group of all of these components packaged together and offered as a single entity for connectivity and managing the entire database. It offers unified endpoint, essentially to, it's a single access point for clients to connect to the database. Let's look at Amazon Aurora's limitless pros and cons. Essentially, limitless service enables horizontal scaling for reads and writes within a region, and it increases the write throughput, right? It also ensures transaction consistency and by distributing data and query across multiple serverless instances. Some of the limitations of these services are it is limited to single region, and it doesn't support global indexes and foreign key across shards. Due to its design limitation, it cannot support serializable isolation. It also means no distributed locks for strict transactions, right? So that is something developers need to be aware of. It doesn't support geo-partitioning. Again, the use cases like data residency applications are expected to have that logic built at application layer. In a nutshell, this provides sharding and horizontal scaling of reads and writes over RDS and serverless V2 services, but with the limitation of lower PG compatibility and lack of geo-partitioning feature. It is best suitable for unpredictable workloads with unexpected traffic bursts. And it is good fit when your application is serving all users within a same region. It is suitable when some downtime is acceptable for non-critical workloads like social media feeds and IoT sensor data, similar to serverless V2. Now let's look at Aurora DSQL architecture. This is a serverless distributed SQL offering announced by Amazon recently in reInvent. It is in a preview launch currently. This is Amazon's first attempt to offer a true distributed database across regions with auto scaling and high availability. It provides active cluster across multi-region. As of now, it supports at most only 2 linked regions. This could change in GA. It means it supports only 2 regions right now. Offers 2 regional endpoints, one for each to increase availability and support concurrent read and writes for each region through these endpoints. Also, this architecture creates a 3rd region called witness region that stores all transaction logs between these linked regions to help with availability and durability. However, this witness region is not accessible for users. Users cannot connect to this. And also DSQL supports ACID transactions with strong read-write consistency across regions. That is a considerable improvement from Limitless. This service has a limited Postgres compatibility due to its design choices and trade-offs. We will discuss about it much more in detail in upcoming slides. It uses optimistic concurrency control. It means if conflict happens, such as multiple concurrent transactions updating the same row, it processes the earliest commit time transaction and rejects all other transaction. It means that it's developer overhead to handle this retry logic for failed on conflict transactions at the application layer, and also build exceptional exponential backup or jitter logic at application layer, and it all developers overhead now from the DSQL design. Let's look at DSQL at component view. It has a front end. This handles client connections using PG protocol, manages the transactions and sessions, and directs connections to appropriate instance underneath. DSQL reuse the Postgres engine for query processor for query processing, rewriting, execution, planning, and execution. And this service also offers a distributed journal service that ensures durability and persists transaction intents before writing to the persistent layer. And this also has a persistent layer that stores changes applied from journal layer and distributes across AZs and presents as a single volume for a query processors. Let's look at some pros and cons of DSQL. This service offers first Amazon Aurora's multi-region synchronous cluster. It is a serverless and automatic horizontal read-write scaling service across regions. It supports zero downtime patching. However, some limitations are, first of all, this is still in preview release, and it has a limited PG compatibility, partially due to design choices and trade-offs, and also maybe because it is in preview and it could improve in GA. We need to wait and see. There are some additional developer overhead due to some design choices, like limitations on 10K row limit, snapshot isolation level only support. We will discuss this in detail in the next slide. This service doesn't support a multi-API as of now. It supports only Postgres API. DSQL doesn't support geo-partitioning. Again, data locality or data residency use cases are not supported out of the box. Applications or developers need to manage this at application layer. It supports AWS only. So users who are building cross-cloud applications or private cloud or on-prem applications, this service may not be a good fit. Let's look at where this is best suitable, right? It's good fit for unpredictable workloads with sudden traffic bursts, similar to the Limitless. It handles well through its on-demand scale up and scale down to zero features. And it is very good fit when high volume transactions apps like financial transactions, ML models, etc. And it is also good fit for new serverless applications that don't need advanced Postgres features. So that's something to be aware of. Let's look at what are those additional overhead for developers that I mentioned earlier. Due to the design choices made in a DSQL service, currently transaction size limit is set to 10K rows. When I say 10K row limit, it is not just for the insert operation, it is applicable for other DML operations as well, like deletes and others. So it requires developers to code to batch the allowed size limit in applications and to handle various situations, right? However, to note, the limitation is bigger than it sounds for the developers, simply because 10K limit is not fixed. The limit can change when you simply add indexes. For example, creating 2 indexes can drop that 10K limit to 3K rows limit, right? So it really varies. So the possible combination of various paths and criteria that developers need to think is way too complex to handle at application layer, all of this logic. DSQL also offers only snapshot level isolation. While it could improve the performance, but the trade-off is existing applications migrating from Postgres, that is read committed snapshot level support, to DSQL. This supports only snapshot isolation level. So the developer's responsibility to make the change and also add additional code at application layer to handle all the repercussions because of the change, right? This hurts the developer productivity hugely.
And I think just to add to that, Anand, there are other restrictions like no support for foreign keys. So that's another area where it needs to be handled by the developers. So it just requires a different programming model, a different mental model for developers to be aware of while developing.
Totally. With that, I would like to hand it back to Shreyas to walk us through the similar feature comparison with YugabyteDB. Shreyas, back to you. Thank you.
Thank you so much for the great overview, Anand. So let's talk YugabyteDB and see how the architecture differs or is similar to DSQL in some ways, and we'll also go over some of the feature differences between the two databases. So one thing that's unique about YugabyteDB is its pluggable API layer. So at a high level, I can divide the architecture into 2 parts. The top half is the query layer, which is pluggable, and we support 2 different APIs right now. So one is a relational API, which is based on Postgres, and the second one is a non-relational or semi-relational API based on Cassandra. Right. So in the same database, you get 2 different APIs to deal with. And due to the pluggable nature of our architecture, it opens up the possibilities for us to support more APIs in the future. The bottom half is the distributed transactional storage layer. That's the secret sauce for Yugabyte, where we use Raft consensus protocol to coordinate the operations across multiple distributed nodes. We support distributed transactions, and this layer also takes care of automatic sharding and partitioning of your data. It also takes care of making sure that data is properly load balanced across different nodes to avoid single points of bottleneck. And then the fact that it's not tied to any particular infrastructure vendor or infrastructure provider makes it available on the common public cloud providers like AWS, GCP, Azure. You can even deploy it on-prem, on VMware Tanzu, Kubernetes, or bare VMs, or even bare metal. So it provides you more flexibility. Let's dive a little deeper into the guts of this architecture and try to understand what's going on. So the top layer or the query layer reuses the Postgres source code. So it's a Postgres fork based on Postgres 15 as of now, which provides you the access to advanced Postgres features, which we are going to cover on some of the next slides. And that allows you to lift and shift apps which were designed for Postgres, some of your existing applications, seamlessly over to Yugabyte as a drop-in replacement with minimum changes. The storage layer is derived from RocksDB. It's a modified version of RocksDB. We call it DocDB. And that layer takes care of distributing your data to avoid any single points of failure in the system. And it can also intelligently distribute, shard, and replicate that data depending on your application's requirements. So we'll talk about some of those details on the further slides. We use Raft-based consensus protocol. And Yugabyte is designed to work on commodity hardware as well. So which is why we use hybrid logical clock, which means it combines the physical wall clock time on every node with a logical counter, and that gives it the ability to tolerate higher clock skew across different nodes, because it's hard to synchronize time perfectly across a distributed system. So using the hybrid logical clock provides tolerance to the clock skew. And then YugabyteDB also integrates with Amazon Time Sync. So if you are running it on a hardware which supports precision hardware clock with clock skew down in microseconds, then you can take advantage of those additional hardware features, and it improves the latency and throughput of the system. Due to the automatic sharding and replication, you can scale linearly. So if you need more juice, you basically just add more nodes, right? So it scales horizontally. You can also scale vertically, but you have both the choices to you. And one unique thing is every node participates in reads and writes. So this does not suffer from the same single writer bottleneck that Anand was talking about for Aurora Serverless. And you can also spread these nodes across different AZs or different regions, even different cloud providers, right? So it gives you the ultimate resilience by extending the failure domain flexibly. Another thing is it has a configurable replication factor. So as Anand mentioned, DSQL is limited to 2 linked regions, which means it can tolerate failure of a single region. If that goes down, you can fail over to the other region and your database continues to work. With YugabyteDB, you can configure a much higher fault tolerance. So, if sometimes your application is so mission critical, you just don't want to be sure, you want to be doubly sure. So you can even design it to handle failures of more than one cloud regions and so on, right? So that's configurable replication factor. You can change it the way you want. Yugabyte also believes in giving more flexibility to the developers. So the consistency levels are tunable. We'll go into some more details further. But if your use case only warrants eventual consistency, you can use that. If you do need strong consistency across regions, you have option to do that as well. So it provides you a lot of flexibility in without forcing you to make certain choices in your application. So let's take a look at some of the key highlight features which separate YugabyteDB from rest of the distributed SQL offerings here. The first one is high Postgres compatibility, right? If you are moving any existing application over from Postgres to a new distributed SQL database, it's important that you minimize the application changes required. And due to the limited support of Postgres, this is true mostly for DSQL. You find it hard to move lift and shift applications, existing applications to DSQL, which is not a problem for Yugabyte, right? So Yugabyte supports all the advanced features like stored procedures, UDFs, triggers, user-defined types, foreign data wrappers, and so on. This is partially due to the virtue of its architecture. So we are literally reusing the Postgres code. So we get, all the benefits of staying compliant with not just the wire compatibility, but even the runtime behavior. It allows us to support Postgres extensions as well, and we have qualified and we support the commonly used Postgres extensions. There are a few caveats here which I'm going to mention on the next slide. Now, Yugabyte can do what Aurora DSQL does, in the sense it can support the snapshot isolation level, which uses optimistic concurrency control. But Yugabyte also supports read committed, which is the default isolation level for Postgres apps. And that gives you the pessimistic locking, right? With wait on conflict kind of behavior. So Yugabyte gives you both the options. Depending on your use case, you can choose whichever one works for you. And it also supports the serializable isolation level. So lots of flexibility built in there. And one thing that's unique about Yugabyte, and it's not true for many other distributed SQL databases, is support for global indexes and foreign keys. This allows you to use referential integrity even in multi-region situations. And this is a problem for DSQL as well as of now. So how do you compare the Postgres compatibility in an objective way, right? So there's a third-party benchmark for checking the Postgres compatibility. It's called Postgres Compatibility Index. It's available on GitHub, and you can try it out on your own machines. So when this was run most recently against both distributed SQL, Aurora DSQL, and Yugabyte, you can see the difference in the score. This is based on the supported features, right? So Yugabyte scored a high score of 85%, which means 85% of Postgres features work as is without any modifications to your application. And then for DSQL, it was still a very low score. Now, we do acknowledge that the service is still in preview, so this might go higher as the service becomes more and more mature. But having said that, as of now, there are significant restrictions around what you can and what you cannot do. So currently in DSQL, you cannot do materialized views. There's no support for temporary tables, triggers, table spaces, UDF, sequence. The list is pretty big. It also doesn't support foreign keys and so on. And there are also restrictions on the DDL and DML statements that can be run. So overall, this is an important factor for you to consider if you're moving existing applications which might need these features. The next one is mostly around doing more at the database layer, right? So one common scenario, if you have users all across the globe, is the data for European users must stay in Europe for GDPR, and use the data for some other geography must stay in the same geography, right? So there are local residency laws cropping up every day in different regions, and it's an additional overhead for developers to deal with this at the application layer. YugabyteDB provides a built-in support for data residency. It uses the Postgres native construct of table spaces, and that provides you the control over how the data gets placed, right? And that makes sure that not just for the primary database, but even for your backups and restores, the data for European users will stay in Europe, and you don't have to do a lot of complex coding around this. You basically just create the table spaces, partitions, and then you can assign one of the columns in your schema as the column to partition this data by. And then Yugabyte will take care of automatically partitioning this data and spreading it across while honoring the local data residency laws. This is also useful not just for data residency. This is also useful for providing low latency access to the users regardless of where they are on the globe, right? By moving the data closer to the users, you can do the writes and reads in the closest region to your users, and that optimizes the latency artifacts, and it gives them a consistent user experience. Usually, if you're a database architect or a developer trying to choose a database, there's a very top-level fork that you have to make, right? So, I like the scene from Matrix where you pick the blue pill or the red pill, right? So you pick a lane, you can do either relational and sacrifice on the horizontal scalability of NoSQL, or you can pick NoSQL for its easy scalability, but then you have to sacrifice the relational features. With YugabyteD, you can get both best of both worlds, and you can do SQL or NoSQL in the same database. For SQL, we support Postgres API, and for YSQL, we currently support Cassandra API. There's no tie-in or there's no specific tie-up with a particular infrastructure provider or infrastructure type with YugabyteDB. You can deploy it on multiple clouds. You can deploy it on hybrid clouds. You can have a completely air-gapped kind of deployment, or you can deploy it on your own data center. There's a big trend happening with large enterprises right now around cloud repatriation. So all of those trends are fully supported by Yugabyte, and it doesn't create any kind of lock-in for you in the long term, which allows you optionality. And then finally, last but not the least, it's open source. So it's the core database is available under Apache 2.0 license. We do not cripple our database by adding feature limitations or any usage restrictions for the open source version. You can use it the way you like. We mostly charge for our database as a service offering, which we will cover on the next slide. And there are no feature limitations or usage restrictions for open source. We have a very strong open source community with 10,000 plus members. And it's a very active and thriving community where you can go ask for help and people are going to help you. And you can find answers to all your YugabyteDB questions very fast. So all in all, Yugabyte is truly committed to open source, and we fully intend to keep it that way. So YugabyteDB mostly makes money off of the database as a service offerings, and we call our database as a service YugabyteDB Aeon. There are two different flavors. First is it's a fully managed variant where you can put the data on Yugabyte's cloud. It can be hosted on AWS, Azure, or Google. And the other option is bring your own cloud. If you're dealing with sensitive application where the data must reside in your own account, in your own VPC, we fully support that option as well. And you can basically keep the data plane you can keep the data in your own account in your own data center, but Yugabyte personnel can manage it for you for a fully managed experience. And then if you do have the resources and expertise and time to manage it on all your own, you can go for the self-managed option, or you can even go for the open source option. So we give you all the flexibility that you need. So all in all, let's do a roundup of features, right? So Yugabyte has an active multi-region architecture similar to DSQL. It has high Postgres compatibility because it's reusing Postgres source code. DSQL also reuses the Postgres engine, but the Postgres compatibility is low, mostly because of the other design choices and because it's in preview at this point. YugabyteDB supports zero downtime upgrades. So all the database upgrades, whether it's a minor version upgrade or a major version upgrade, are done in a zero downtime fashion, where we do it in a rolling manner. Your application continues to stay connected to the database, and we also support rollback, right? So in case you move to a newer version of the database and you find out for whatever reason it breaks your application, you do need to you do have the ability to roll back that upgrade and go back to your previous version. So all of that makes it attractive for mission critical applications. Also about the built-in features for data residency that just makes the life easier for our developers by not having to add that in the application layer. You get plenty of options in terms of how you want to replicate the data. You can do it in a synchronous fashion. You can do it in an asynchronous fashion. So you have the choice. It's multi-API, so you can do SQL and NoSQL both in the same database cluster. You can deploy it anywhere. There's no lock-in, cloud agnostic, and open source. There are some limitations with YugabyteDB currently. So we do not have a serverless offering. So it's not ideal for workloads which might need to scale down to zero. It's mostly useful for applications which need to run over a significant amount of time. So it's not the best suited for ephemeral workloads at this time. And currently, there's no support for geospatial indexes. This is something we are working on actively, but that's a current limitation to be aware of. So what are the suitable workloads for YugabyteDB at this point? Any workload that may experience rapid growth and might go through unexpected traffic spikes is a good candidate. We have some examples, real world use cases to share later, which will exemplify these workloads. Another one is high volume transactional applications. This could be financial transactions, payments, e-commerce, gaming. All of those are great use cases for high volume transactional applications. And they work beautifully on Yugabyte. It's also important for mission critical workloads that just cannot take any downtime, right? As we saw, even the zero downtime patching feature in Aurora is not truly zero downtime. There are caveats to that, and there are cases where you might have several minutes of downtime. It's also suitable if your application has global user base, users connecting from all over the globe. This is probably a good choice. And if your workloads need to run in a non-cloud or hybrid cloud or a multi-cloud environment, then it's ideal. It's also ideal for brownfield or existing applications, which are migrating over from Postgres. Because of its high Postgres compatibility, you need to make minimal changes, and that avoids a lot of back and forth while doing your DB modernization play. It's also suitable for new applications that are looking for a cloud native scale and agility from get-go. So with that, let's take a look at the final comparison, right? So we're going to compare Limitless, DSQL, and Yugabyte because the rest of the offerings are not truly distributed SQL. So it would be an unfair comparison. So we are mostly going to keep it focused on these three options. So with Limitless, this is the feature scorecard. We have different access depending on what the feature set is. So on the Postgres compatibility, Aurora Limitless scores a high score because it's reusing the Postgres engine. There are some changes around how you create the sharded tables and the reference tables. You need to set the session variables, so on. But those are some minimal changes to Postgres syntax. Also, it gets a moderate score for availability, mostly because it's a single region restriction. You cannot span multiple regions with Aurora Limitless. And in terms of availability, there are still operations like major version upgrades. There are operations like OS upgrades, which cause downtime. So it doesn't get the high score for availability. On the scalability aspect, there are restrictions on how many DB shards you can create per AWS region and so on. So, due to those restrictions, it gets a moderate score for scalability. And then it only supports Postgres API. So, on the multi-API access, it basically gets a low score, just one API. And geo distribution, there are less features baked into the database itself to support the geo-distributed use cases. So, as this feature set grows, maybe this rating will go up. But, right now it's, low due to those restrictions. Let's take a look at DSQL. Now, we fully realize this is in preview. So, some of these scores might change as the feature moves towards its general availability. But right now, the Postgres compatibility is pretty low, given all the restrictions. In terms of availability, it scores very high marks because it has a multi-region active-active kind of architecture similar to Yugabyte, and it can handle zero downtime upgrades and so on. In terms of scalability, there are some restrictions, like you can only do 10,000 rows per transaction, inserts, deletes, DML operations. They all have the same restriction, and it gets weird with indexes. So due to some of those reasons, the scalability is on the lower side. Because of those restrictions. And then multi-API, there's only support for Postgres, so hence the score. And then geo-distribution, there's still no support for geo-partitioning, but they do add multi-region capabilities, so the score is moderate here. So that's how the DSQL fares on the feature set. And then for Yugabyte, there's high Postgres compatibility because of the use of Postgres source code. Availability, we provide a lot of options and features to make sure there's truly zero downtime for mission critical applications. In terms of scalability, we support some of the biggest workloads by linearly scaling the load by just adding more nodes horizontally. So that's a high score as well. And then for multi-API, there's a high score because of the pluggable API or pluggable query layer. So currently we support Cassandra and Postgres, but we can even add more APIs in the future. Geo-distribution, we are scoring higher because there's built-in support for geo-partitioning, and there are multiple replication options, synchronous or asynchronous, depending on where you want to deploy your application. So with that, let's look at some of the real-world use cases to get a sense of what kind of use cases are powered by Yugabyte today. So the first one is Paramount Plus, the streaming application. And if you watched Super Bowl last year, 2024, then Paramount Plus exclusively streamed Super Bowl last year, and YugabyteDB was acting as the backend for the user authentication for this use case. And this was a pretty significant workload given the scale. Streaming at Super Bowl scale is no mean feat. And then while making sure there's no downtime, there's no performance and scalability problems for the end users. So Paramount Plus was able to achieve good results with YugabyteDB, and they did this not just for the Super Bowl, but also some of the peak events like AFC playoffs, the launch of Top Gun Maverick for all the Tom Cruise fans out there, and so on. So YugabyteDB provided high level of resilience and sub 30 millisecond latencies for the transactional workload. And it was also easy to migrate away from MySQL to YugabyteDB. And then, it worked extremely well with some of the ecosystem integrations, and they are also using the data residency features. Another example, and this is from the NoSQL part. So Paramount Plus is using the SQL API, the Postgres API. And this is an example from the other side of the API set, which is the Cassandra API, the NoSQL API. So General Motors uses YugabyteDB as the backend for all the telemetry data collected from its connected cars. And there are, every GM vehicle running everywhere sends all the events back to YugabyteDB. It's spanning multiple data centers and 3 availability zones. And the performance speaks for itself. So, GM is able to achieve sub 3 millisecond latency for its writes, and even lesser latency for the reads. This is a resilient system, which means it's tolerant to failures. And then in terms of the cost saving, this has also saved GM quite a bit of cost by reducing their hardware footprint, because Yugabyte basically packs the data more densely as compared to Cassandra, and that allows you to run the same kind of workload with similar characteristics but with less number of nodes. So it's also a good replacement for data stacks or some of the other Cassandra deployments out there. So having said that, I promise that there might be a surprise for you at the end. And so thanks for sticking around. So first of all, join our open source community. We would, be very pleased to have you join the community where you can ask all sorts of Yugabyte questions. Any questions that we may not be able to answer on this webinar today, please feel free to join the open source community. There's a QR code here. You can scan it and quickly get into the community. Exclusively for the viewers of this webinar, we are also giving away a 30-day free trial for YugabyteDB Aeon. Use the promo code Better Together and start your free trial, and that's going to give you a 30-day free trial with $3,000 of credits. So that's just our token of appreciation for you taking out the time today. And then if you would like our team to walk you through some of the advanced features of Yugabyte, please use the schedule a demo link, and we would be happy to do the walkthrough for you. So with that, that brings us to the end of this webinar. Let's do some Q&A. This is a good time to answer some of your questions. So we are going to take a few questions live here. Okay, so one question is, when it can't scale automatically, do we need to predict and over-allocate the resources? So though Yugabyte does not have a serverless offering, right, you can quickly scale out your nodes. Usually it takes, within 10 minutes, you can add new nodes and they start accepting new connections. So, it does scale pretty fast in those situations. Yes, over-allocating the resources is an option if you can predict your workload. If you already know the peak traffic that you might expect, you can over-allocate the resources in some cases based on the anticipated traffic. But also if you have to react to unforeseen demand and you need to expand quickly, usually you can new nodes get added to the cluster and start accepting connections within 10 minutes. How many nodes GM uses? I'll have to get back to you on this one. I don't have the details off the top of my head, but I can get you the details offline. Okay, Jim, thank you. We are glad you found the session useful. Is there a doc for Kubernetes deployment? Yes, we do have a doc for Kubernetes deployment, and maybe someone answering the Q&A. Could you please guide Jim to the right link in our documentation? Thank you. Okay, a lot of appreciation on the chat. So we also appreciate your time. Thank you for joining. It's we are all fans of distributed SQL, and we appreciate Amazon getting into this space. It has just rejuvenated the interest in distributed SQL, and we are looking forward to the distributed SQL feature. Okay, I think we are at time, so maybe we can take a few more questions and then. Okay, so there's a question: are there any customers using single cluster for both SQL and NoSQL workload? Yes, we do have customers using this. If you go to our website, you'll find a case study from Admiral, and Admiral is an example where they're using both SQL and NoSQL in the same cluster. And there are others too. This is just the one that I have off the top of my mind. Okay, thank you, Sampath. Thanks for your time as well. Thanks, Jim. Okay, do you have any airlines customer? I'll have to get back to you on that because I don't want to give out specific customer details on this call. I'll definitely get back to you if you can leave your contact details. All right. Overall, thank you, folks. Thanks for your time, and we will keep the dialogue going. If you're interested in more such comparisons, do drop us a note. Join our community Slack and just provide your wish list. We would be happy to do more comparisons like this in the future. So enjoy your day ahead, and thanks for your time.
Thank you, everybody.